Looking at scientific notation. Scientific notation is a way to represent very large or very small numbers. We have the general form m times 10 to the some power, which we'll call n. M in this example is the coefficient. It's greater than or equal to 1, but less than 10. Okay, so it can be equal to 1, but it can't be as big as 10. It can be 9.9999999, but it can't be all the way up to 10. It's important to realize that all digits in M are significant. N is the exponent of the power of 10, can be any integer, positive or negative. So this number has to be a whole number. It can't have a decimal point in it. The fact that all digits in M are significant is what makes scientific notation so useful in chemistry and physics, because it makes it easy to see which digits are significant and which digits are not. And I'll show you that once we start doing some examples here. So, how do you convert to scientific notation if you know the standard notation value? Well, to get the coefficient, you move the decimal point until there is just one non-zero digit to the left of the decimal point. Then, for the exponent value, you count the number of places that you moved the decimal point. Then you need to decide the sign on the exponent. You can have a positive exponent or a negative exponent. The sign depends on whether the original number was bigger or smaller than 1. If your standard notation was big, if your standard notation was larger than 1, then the exponent must be positive, because you have to multiply by powers of 10 to get back to the original value. If the standard notation was small, if it was less than 1, then the exponent must be negative, because you have to divide by powers of 10 to get back to the original value. So let's look at some examples, because again, explaining it in words doesn't necessarily make as much sense as just doing it. So how do I go to scientific notation from this example? First, remember, my decimal point is implied to be here, even though it's not written. I'm going to move the decimal point until there's just one non-zero digit to the left of the decimal. So I'm going to move it 1, 2, 3, 4, 5 times. So what number do I have here? I'm left with 1.23 when I move that decimal point. Now these zeros were not significant, so I'm not including them here in my answer. I have my coefficient, it's 1.23. But 1.23 is clearly not the same as 123,000. These two numbers are not the same. I have to multiply times 10 to some power to make it equal to 123,000. I'm going to multiply it times 10 to the 1, 2, 3, 4, fifth power. And that is a positive 5 because my original number was big, was larger than 1. This number is much larger than 1, so my exponent is positive. On the other hand, let's look at a number that's super small. This number is going to have a negative exponent because this number is definitely less than 1. Let's follow our procedure. We're going to move the decimal point until there is one non-zero digit to the left of the decimal. So 1, 2, 3, 4, 5, 6 times I move the decimal point. I have 3.260 as my coefficient. Remember, all of these guys are not significant, but this 0 is significant, so I do include that 0 in my coefficient. It is significant, so I am including it there. Times 10 to the, how many times did I move the decimal point? 6. 1, 2, 3, 4, 5, 6. Times 10 to the 6, but that is a negative 6 because this number, my starting number, was small. It was less than 1, and I reflect that less than 1 with this negative exponent. How do you convert from scientific notation to standard notation? The exponent sign indicates which direction you need to move the decimal. And again, using the same logic that we were using before, a positive exponent means that the standard notation was big. So it's going to be an absolute value greater than 1. A negative exponent means the standard notation was small. The absolute value is less than 1. So again, let's do it. Oh, not quite time for examples yet. The exponent value tells you how many times to move the decimal point on the coefficient. The direction is determined by the sign, but the number of times you move the decimal point is determined by the value of the exponent. So let's look at some examples here. Here I've got 10 to the 6th. That's a positive exponent, so that tells me that this number is actually really big. So I want to move the decimal point in a direction that makes that number really big. And then I want to move the decimal 6 times. So I'm going to move it 1, 2, 3, 4, 5, 6 times. Now my decimal point is implied here, but I'm not going to draw it in, because if I put a decimal point here, then I'm saying that this number has 1, 2, 3, 4, 5, 6, 7 significant figures. And it does not. This number only has 4 significant figures. So sometimes you'll see people actually write in parentheses afterwards that this has 4 significant figures. But this takes a lot more time than just writing it in scientific notation to begin with. 2.60 times 10 to the negative 3, that negative 3 tells me that I'm going to make this number smaller than it looks. So I need to move the decimal point in a direction that makes the number smaller. So if I write down the 2, the 6, and the 0, I want to move the decimal point once, twice, 3 times. So this is where my decimal is. So 0.00260 is the correct standard notation for this example. And this answer has 3 significant figures, and we do show 3 significant figures. So that is the correct conversion for that scientific notation example. So it's time for you to pause the video and try these out for yourself, and then come back and check your answers. Okay, so here we're going to go 1, 2, 3, 4, 5 moves of the decimal point. So we're going to have 9.56 times 10 to the negative 5. And we use the negative sign there because this number was small, less than 1. Here we're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. So we're going to have 9.5 times 10 to the 14th. Here we're going to move the decimal, and again, the positive exponent because that number is much bigger than 1. For 52 million, we're going to move the decimal point 1, 2, 3, 4, 5, 6, 7 times. So we get 5.2 times 10 to the 7th. Positive exponent because the number is bigger than 1. Here we move the decimal point 1, 2, 3, 4 times. This number was less than 1, so we're going to say 1.56 times 10 to the negative 4. The number 26, you just have to move the decimal point 1 time, and that gives you 2.6 times 10 to the first power. 0.0015, you move the decimal point 3 times, so you get 1.5 times 10 to the negative 3. 4.3000 times 10 to the negative 6. This number is less than 1, so, the negative exponent indicates that my number will be less than 1. So I have 1, 2, 3, 4, 5. That would be 6 times moving the decimal point. but I still include these trailing zeros because they are significant, so it's important for me to keep those zeros there. And lastly, 3.200 times 10 to the third. I'm going to move the decimal point 1, 2, 3 times. So I'm going to end up with 3,200. And I do include the decimal point there because those zeros are significant. They were shown here, so I'm going to keep them there. We do have 4 sig figs here. All right, so that's going to and from scientific notation.